you eventually learn how to walk. So, ready to go.
All right. Welcome, everyone. We're excited to have you here. This is a big group, so you must be really excited to learn about Pythagoras after that. Welcome to Williams. We're lucky and honored to have Professor Steve Miller here to teach this sample class here. He's an associate professor of mathematics, and he just finished his 7th year here at Williams, having taught at other schools like Brown, Ohio State University, and Princeton, where he earned his PhD. His research interests include number theory, operations research, and sabermetrics. What that means, I don't know. He is the expert.
We'll find out in a few minutes.
And on campus, he's the faculty program director of the neighborhoods and the faculty president of the National Honor Society Phi Beta Kappa. So thank you, Professor Miller, for being here.
Thank you.
Close the door.
You can close the door. And so I believe parents are not allowed to come to this. You know, the word Pythagoras is to make people think you're actually in an academic discipline right now. And you think back to your old geometry days. So this is about sports mathematics. How many people here are Red Sox fans? Congratulations on your admissions to Williams College. Who are the Yankee fans? Amherst College is a fine institution. Okay, so normally I actually wear Red Sox stuff and I go all out, but you know, the way the Red Sox have been performing this year, I've decided to go local. So I'm wearing the North Adams Steeplecats, which is our local summer collegiate baseball team, and the Mount Greylock Regional High School Mounties, which is the high school for Williamstown and Lanesboro. Okay, out of curiosity, how many of you have heard of Bill James' Pythagorean formula? Excellent. So for the most part, you don't need to know too much about baseball to make this talk understandable. I will quickly explain in my mind what parts of baseball you need to understand. If you want to get into some subtleties of the game afterwards, I'm happy to discuss some of that. My son believes he saw somebody steal a base with a ball that landed in foul territory, which I'm a little surprised over. But there are some strange rules in baseball which are not going to really play a role here. What I want to do today is I want to give you a sense of why are you learning all of this mathematics. And so sometimes people look down on sabermetrics, down on applying mathematics to various disciplines, and they say, this is just elementary basic mathematics. Yes, involving billions of dollars every year with people tuning in and watching this stuff far more than people watch the great math debates. Have any of you seen the great math debates? Exactly. So in terms of how deep the mathematics needs to be in order to make great contributions, it doesn't have to be that deep. You already know enough to be on the leading edge of a lot of research. What you need to do is you need to learn a little bit more probability, you need to learn a lot more statistics, and you need to get some sense as to why you do calculus. So out of curiosity, does anybody know why we learn calculus? Yes? The sad thing is this is probably from the Aristotle, Plato, Socrates. It's brown because it has the nature of brownness in it. And this is the way calculus is often taught. It's just, well, we do this, so let's learn it. Just like we learn the quadratic formula, we do problems on the quadratic formula. What I want to give you today is a sense of why we do stuff like this. So I want to acknowledge a couple of people, most particularly my great uncle Newt Bromberg, who assured me I would live long enough to see the Red Sox win a World Series. This talk is joint with some members of my family, Cameron and Kayla. Kayla's over there. They could have been here today, but Cameron decided he'd actually rather be playing baseball with his friends at the beach. So that's where he is right now. He sends his regrets. All right, so I want to talk a little bit about the Pythagorean one-loss theorem. I'm a mathematician, so I use the word theorem. In ESPN and sites like that, they probably are more likely to use the word formula. All right, so the goals for today is I'm going to derive what this formula is, and we'll observe how ideas and techniques of modeling enter into a problem. So again, the idea is there's something in the real world you want to understand. You want to extract the key features from it, and you want to be able to attack it and come up with something reasonable. Now, what will happen is very quickly advanced theory will enter. How many of you have taken a calculus class? Excellent. I'm a little concerned that one of my summer research students who's here right now did not raise his hand, but he did go to Harvard. They actually don't do applied stuff like that there. How many of you have ever done the drowning swimming problem or the drowning swimmer problem? So you have a poor swimmer who's in the water drowning and dying, and you have a lifeguard, and the lifeguard is trying to figure out what's the best path to reach the swimmer in the least amount of time. It's actually the same as the path light takes when it travels from one medium to the other. If you know Snell's law from physics. Most lifeguards do not whip out a piece of paper and start doing the calculus to try to figure out where they go. If so, they don't get hired back. People are instinctively pretty good at knowing roughly what is close to optimal, and for most things, close to optimal is good enough. But if you try to do the drowning swimming problem, very quickly you see some very difficult mathematics entering, such as trying to solve a quartic equation in closed form. There are ways to do this, but a very simple problem leads to some really good, interesting mathematics. A big point for today is there's opportunities from inefficiency. I've got to be a little bit careful because this is being recorded, so if any of you want to play this back later, all I will say is that there are some people in the world who are doing things less than optimally. And if you notice somebody is doing things less than optimally and is not valuing what they have correctly, there are advantages for market inefficiencies. If you don't like baseball, you can always replace these words with words from economics and say stocks, mutual funds, companies. If something is not being evaluated properly, there is an opportunity to make a killing. And the last is there are avenues for further research. So I have been fortunate to work with a lot of great students over the years in problems like this. I've taken students on private tours of MLB parks, met people. Never got to meet a Cy Young winner, but I did get to meet a Cy Young winner's dog, which is something. I also saw the biggest TV screen I have ever seen in my life for the game system the Major League ball players use between innings. And so there's a lot of great stuff that you can do just at the college level. I've supervised senior theses here at Williams. I've taught independent research classes on sabermetrics. And so there's a lot of stuff you can do here. All right, so the goal is to find good statistics to describe the real world. So I had a hunch that I would have a student from Boston here, and so I have modified the talk a little bit in his honor. I'm assuming you can read, but even if I didn't, could you have noticed this? Yeah. Yes. So this is the Harvard Bridge. It's about 620.1 meters. I'm a mathematician. I like things like 0.1. I like to be precise. Does anybody know the other unit people use to measure this bridge? No! Feet is bad. Feet led to the $25 million whoopsies when a Mars probe crash landed because all of the systems were in metric, but one which was in the English, so they miscalculated how much thrust they needed. Thou shalt not use the English system. Okay, yes. Smoots, excellent. So the bridge is 364.1 smoots plus or minus 1 ear. It is amazing what you can do to pledges and fraternities, especially if you go back in time to the 1960s. Now, this was MIT, so the notion of what you do with a fraternity pledge is a little bit different than what you'd see in Animal House, if you know what that movie is. They decided to pick up Smoot and physically move him along the bridge and see how many smoots was it from one end of the bridge to the other. Is this a good statistic or not? No, right? Why not use meters or even feet? Something that everybody else has a sense of. There's nothing you're gaining by measuring it in smoots. When I'm saying looking for good statistics, the smoot is not a good statistic. As an interesting historical note, the Cambridge police were not too amused at the bridge being marked in smoots, and so they would, paint over the markings, at which point the MIT students would repaint them, yes. And so it went on for a while, and eventually a change of heart happened. And now when there's an accident on the bridge, they actually record where the accident was as to how many smoots from the end of the bridge. All right, so what I want to do is I want to talk a little bit about the progression. So this is the very first time I was a head coach of a baseball team. This was my daughter's team 2 years ago. There were players under 4. A lot of fun coaching people under 4 in baseball. All right, this was this year, getting a little bit better. This was my son's team last year. This was my son's team this year. I wasn't able to become a full coach. I'm still working up in the ranks. I got up to dugout manager. This is my highlight of my baseball career. Anybody know what I have on?
World Series ring?
Yes. I actually know a neighbor of one of my father's cousins who has 3 World Series championship rings. I got to wear this one for a couple of minutes. I won't say what I offered in exchange for it, but I am still married and I'm still a graduate of Yale. And I still have my firstborn son. Okay, this is a picture from this year. This is now a tax-deductible trip to Boston because I'm now showing this talk in the lecture. So Clay Buchholz was pitching for the Red Sox. Cameron was very excited. We didn't actually get the ball. The ball actually hit a girl a few rows from us and she was crying. And then the person who got the ball gave it to the girl. And then Cam went up and said, "Can I just have my picture taken with the ball?" So he's young enough that, so for him, this is still a good highlight of the day. It was close enough. I got to hold the ball. I want to get to something like this where we can be involved in the game in a non-trivial manner. This, to me, is not great involvement. All right, what are the key parameters for what we're going to talk about today? So RS observed is the average number of runs scored per game. RA observed, average number of runs allowed. You always want your variable names to be descriptive, so you can quickly glance down and see what's going on. RS runs scored. And then gamma is going to be some parameter. It's going to be constant for different sports. You can apply this to basketball, to football, to hockey, but the analysis is much better in baseball. And I'll tell a little bit more about that in a moment, or actually have you decide. So Bill James is considered the god of the subject. And for a long time, he was a one-man show looking about how mathematics and statistics can be used to predict things in baseball. And what he noticed is a really good prediction of a team's win-loss percentage, the number of wins divided by the number of games, is their average number of runs scored to the gamma over runs scored to the gamma plus runs allowed to the gamma. And back when he was doing this, it was kind of hard to do these calculations by hand, so he took gamma to be 2, which does a pretty good job. Nowadays, the best value of gamma is about 1.82. Anybody know why this is called the Pythagorean one-loss formula? No, baseball is played in a diamond unless you either draw a line from second base to home or you talk about the Red Sox outfield. Where's the triangle?
Oh, I meant the RS.
Oh, no, it's not physically a triangle, but there is, in some sense, if you take gamma equals 2, there is in some sense a triangle lurking. Why does this kind of look like something that should be called Pythagoras? Yes?
Because if you have RS, OBS times, well, to the power times the constant, which is the proportion of games won,
Right.
that could be like the hypotenuse, and then
Yes. So if you look at these as the two sides, it's a sum of squares. The level of mathematical sophistication was not that high, but it's a good name. It looks like sum of squares. People think when they see sum of squares, they think of Pythagoras. So it's called the Pythagorean one-loss formula. Any idea why this does a much better job of predicting a team's winning percentage in baseball than a sport like football? More games. There's about 10 times more games in baseball than football. And so the more data you have, the more likely you are to make good predictions. So just as an example, back in 2009, the Sox were 95 and 67, scoring 872 runs, allowing 736, for a predicted record of 93.4. Not surprisingly, I'm going to choose a year and numbers where it comes up pretty good. This is a little bit cooked. The Yankees were 103 and 59, but predicted to be 95 and 66. So they were significantly outperforming the prediction. So one of the big questions you have when you get a formula like this is, how good is the formula? How much should I trust it? What should deviations from the formula mean? For the Red Sox fans here, do you remember 2011?
Yeah.
So 2011, the Sox and Tampa were tied going into the last day of the season. According to Pythagoras, we actually should have made the playoffs that year. This was the year the Yankees allowed 7 runs to Tampa in, I think, the 7th inning. You can't prove that the Yankees were just throwing marshmallows down the middle, but when you're off by 1 or 2 games, this can have huge consequences. The Red Sox missed the playoffs that year. We're talking millions of dollars in revenue to the teams. So in terms of how accurate these formulas are, it's going to be very hard to get something more accurate than even 1 or 2 games, and that can be enough. All right, why do we care about something like this, even if we can't get as accurate as 1 or 2 games? What if only about 4 or 5? Well, here are 3 big reasons. One is extrapolation. You can use it to see how a team has started the year. How do you expect them to do as the year progresses? A couple of years ago, if you need an example in baseball, the Baltimore Orioles typically are there for you. They had one year where I think they were 19 and 1 in one game, in games decided by 1 run. And that pushed them into the playoffs. And so in some sense, the Orioles were a very lucky team. Or they did a phenomenal job managing their bullpen and managing their resources. So one of the things you can do is you can see how a team is doing at the start of the year and see where your threat is. A couple of years ago, the Yankees started off, I think it was 23 and 27, below 500. And the Yankee management has to make the decision, should we give up on this season, conserve our resources, and go for next year? Or are we just underperforming, and are we really a much better team than our record indicates? And all the statistics said the Yankees were much better than their record indicates. It's just a string of bad luck. And the Yankees made some big moves, including getting Roger Clemens, and they did make the playoffs. So one of the advantages of something like this is if you have some rough sense of how a team is doing, you can then figure out where you want to devote your resources. Another reason is evaluation. So if a team is consistently overperforming or underperforming, this could be attributed to being managed well. Is that maybe you have a manager who has a good sense of how to use the bullpen, how to use the players. Another example is when you're trying to figure out how valuable is a player to you. The value of a player is not independent of the team. If you are on a really good team, let's say you're on a team that scores a lot of runs, adding one more player who scores a lot of runs is not going to be that valuable. Your team's already scoring a huge number of runs. But if you're on a team that has a very weak batting order, maybe adding that player is worth a lot more. Certain wins are worth more than others. If you just make the playoffs, those last few wins are worth a huge amount. So when you're trying to figure out how much money do you want to spend on a player, it's not just a function of how good that player is. It's how good will your team be with the addition of this player? What is the marginal benefit, for those of you who like economics, of getting this player? And it becomes extremely important with the negotiations. The last one is advantages. Basically, you want to try to figure out which statistics matter. Many of you have probably seen Moneyball, heard about Billy Beane, seen the movie, read the book. One of the things he was great at is he had a willingness to listen to people as to which statistics really mattered. People were overemphasizing batting average, how many hits you have per at bat, versus on-base percentage, which was essentially hits plus walks. People were not valuing a walk high enough. And he was able to take advantage of this and go for players who were being undervalued by the market. Okay, so this is a question where you need a little bit of baseball knowledge. Who knows what a save is in baseball? What is a save?
It's when a pitcher comes in and the game's within 3 runs and they pitch to the end of the game and their team wins.
And when you say within 3 runs, their team is winning.
Or 4 runs and the base is loaded.
There's another way to get a save. Anybody know the other way to get a save? If thou pitchest the last 3 innings of the game, thou shalt be credited with a save, irregardless of what the score is. So a couple of years ago, the Baltimore Orioles were playing the Texas Rangers. After 6, Texas was up 14-3. My grandmother, may she rest in peace, might have been able to pitch 3 innings and hold on to that much of a lead. You could alternate home run out, home run out, home run out, and still win the game. When you hear the word save, you think dire situation. You think the game is on the line. Texas brought in a relief pitcher who pitched the final 3 innings. While he was pitching, Texas scored 16 unanswered runs. The final score was 30 for Texas, 3 for Baltimore, and he gets the save. Billy Beane was phenomenal at having certain of his pitchers become save machines. You want my star reliever? Oh, well, I do need a second baseman. And so if you know which statistics people value and you know which statistics really matter, you can, well, be very careful because this is being recorded. So I will leave it as an exercise to you to think of what you can do. All right. So I will skip that. I will go into some quick introductions. Anybody recognize this image? What's this from? Price is Right. Good. I'm just curious to see which shows I still watch and you guys still watch. All right, so what I want to do is I want to observe some kind of data from the real world, some kind of model maybe for runs scored, heights of students, hopefully not scores in my calculus classes, and you'll try to come up with some theory that will predict what's going on. So I want to do a quick probability review, or introduction if you haven't seen it before. So x is a random variable with density p of x. What this means is I have a function p, which is greater than or equal to 0. Its integral from minus infinity to infinity equals 1. That means the area under the curve equals 1. And the probability it takes on a value between a and b is just the area under the curve from a to b. So for those of you who've taken integration, how many of you have taken integration before? Why do we care about integration? It's a little disconcerting that you've all taken a class and you can't say why we care about the class you took. Why do we care about integrating? Yes?
It allows us to sum up instantaneous quantities.
Why do we care about summing up instantaneous quantities?
Well, if you take the whole thing and the probability of that is 1, each a part of it,
Yep.
and you integrate that, you can get a probability.
Excellent. Integration gives us probabilities of events. And so, oh, interesting. So on my slides, it actually has things highlighted. So the mean is the average value. The variance is how spread out it is. The area under the curve from A to the B, which is not projecting here, is the probability I take on a value between A and B. We care about integration because it gives us probabilities of events. It allows us to talk about the likelihood of something happening. The mean is just the average value. The variance is the spread out. So the larger the variance, the more things are spread out. Anybody who's taken an ultra-competitive class knows all about means and how you're doing. All right, the last one is independence. Knowledge of one random variable gives you no knowledge of another. If that is true, then we say the two events are independent. So as an example, how long this lecture takes, I think it's supposed to be 50 minutes. I'll try to keep it to around 50 minutes. The amount of time I take and how the Red Sox do tonight, probably independent. So we have Price is Right fans. Who's watched Price is Right? So one of the things in Price is Right is you have the big wheel where you have the numbers from 0 to $1 in increments of 5 cents. And whoever gets closest to $1 without going over wins. So you're the first person, you spin, and then you spin again. Are those two spins independent?
Yes.
If you just spin naively, close your eyes and just spin naively, they should be independent. But in practice, are they independent? No, you're trying to get close to $1. So you might try to give it just the right amount of spin so that you get to the part of the wheel you want to be. So you've got to be very careful as to whether or not events are independent or dependent. It's a lot easier to analyze things that are independent, so we will frequently just lie and say things are independent and hope the dependencies are not too bad. And then in more advanced classes, you learn how to deal with issues like that. All right, guidelines for modeling. So here are the two principles of modeling, because this is all the time I have. The model should capture the key features of the system, and the model should be mathematically tractable. Anybody ever watch the Charlie Brown baseball cartoons? All right, so this is where our TV histories diverge. His team is horrible. It's basically a litany, in whatever can go wrong for his team goes wrong. It's very, very sad and tragic. Snoopy's the only one who has any baseball skills, I think. He's very sad because these are conflicting goals. These are conflicting ingredients. You want to capture the key features of the system. Well, the more things you capture, the more complicated your model is going to be, and the harder it's going to be to deduce anything useful. So I want to suggest a possible model. So just to make sure we're all on the same page for baseball, Red Sox good, Yankees bad. If you want a little bit more information, whoever scores the most runs in a baseball game wins. Okay? So here is one possible model for a baseball game. The runs scored and runs allowed are independent random variables, and they're given from some probability density function. And if this is the case, then we can calculate the probability of a team winning or losing as follows. If we do the integral approach, we want to integrate. This is the probability I score x runs. This is the probability I score y runs. I want to go over all pairs where x is greater than or equal to y, because then I'll win. And with continuous variables, the probability that y is exactly equal to x is negligible. So I know many of you haven't done multivariable calculus. Just do single variable calculus twice. All right, there you go. You've learned multivariable. The other way is I could do it with sums. This is the probability I score I runs. This is the probability I allow j runs. So if I sum over all pairs where j is less than I, this will be the probability that I win. Which model do you think is better for baseball? The continuous model or the discrete model? If you had to model a baseball game. Did anybody see the Red Sox score last night? I think they lost pi to e. No, that was 2 days ago. No, Red Sox actually had a day off, which was good. How many teams have lost by a score of pi to e? Yeah, no teams have ever lost by pi to e. As bad as the Sox season is this year, and it's bad, they're not going to lose pi to e. So this suggests that maybe the discrete approach is better. We're not going to see numbers like square root of 2 coming in as a score in a baseball game, so why not do things discrete? Can anybody give me a reason why we might want to take the continuous approach?
Yes? Well, if you have a formula for both functions, then it seems easier because you just integrate twice rather than doing a lot of sums.
So how many of you have taken an advanced class in summation theory? I have to put my hand down as well. We don't have classes in summation theory. Sums are hard. But there's a lot of integrals that can be done nicely in closed form. And so the hope is that this might actually lead to a more tractable expression than this. And so it's a little bit of a lie, and this will allow the possibility of the Red Sox losing by pi to e. But I'm willing to allow it, and it will lead to a nicer formula. So here's my method. I'm going to model runs scored and runs allowed by independent random variables. This is the point where I look at the clock and I see how much time is left to give you time to shoot down this model. This is a bad model, it has lots of issues. Can anybody give me any flaws, any difficulties, any worries they have about this model? You need to have a little bit knowledge of baseball. What might be a little bit troubling about this assumption? They might not be independent. Can you give me a way that runs scored and runs allowed might not be independent?
Well, if you're down by a lot of runs,
Okay. Well,
switch up your strategy.
so you might switch up your strategy.
A pitcher down or up by 6 runs might move to a few pitches you wouldn't normally throw.
Yeah, you might just want to try to get the ball in play.
If a team's up by a lot of runs, they might put in a worse reliever who will give more runs to the other team.
It's more than might. Anybody know who Remlinger is? Exactly. He didn't last that long. He was with the Red Sox for a while. And I remember a couple of years ago when he was brought in to pitch, one of the things they give you is the pitcher's ERA when he comes in. That's how many runs they allow per 9 innings pitched. They had 3 dashes by his ERA. Do you know why they had 3 dashes by his ERA?
Because it was embarrassing.
No. Well, I mean, it was embarrassing, but he had not recorded an out. It was division by 0. He had allowed runs as a Red Sox. He just hadn't gotten anybody out yet. And you are not allowed to divide by 0. Even the Fox News sportscasters, will not divide by 0. So they just wrote 3 dashes for his ERA. The Sox were up 10-3. It was the 9th inning. They don't want to waste a good pitcher in a situation like that. He proceeded to give up a grand slam. He did get 3 outs. He did get the 3 outs and get the save. My feeling is you should not really get the save when you come in with a 7-1 lead and only pitch 1 inning. So that is absolutely the case that you can have changes in who's going, changing in your scoring frequency and the runs allowed frequency based on the game state. There's another problem, though, with this idea of runs scored and runs allowed being independent. And to see this, we have to go to the greatest, I think, man in the history of the world, the former commissioner of baseball, Bud Selig. He has protected us as a nation from a catastrophe ever occurring again. Does anybody know what Bud Selig has done to protect us?
Read the All-Star game important?
It's related to that. It's related to an old All-Star game. Anybody know what he did? Something happened in an All-Star game several years ago.
He called it a tie, right?
There was a tie in an All-Star game. Now, we only have about another 20 minutes left. I don't have time to go into why it would be so bad for a baseball game to end in a tie. I know this can happen in other sports. It would just trust me that it would be a catastrophe if this happened in baseball. So we will now make sure we have rules in place. We have a system. No baseball game will ever end in a tie. So I am thinking of a very special Red Sox game from several years ago. The Baltimore Orioles scored 5 runs. What can you tell me? The Red Sox did not score exactly 5 runs. This was the Mother's Day miracle game. It was 6-5 Red Sox. The Red Sox won on a walk-off error. Your Baltimore completely collapsed in the bottom of the 9th inning. They blew a 5-0 lead. But as soon as you're told the Red Sox, as soon as you're told the Orioles, you're going to always there for us, have 5 runs, the Red Sox did not score 5. So they can't be independent because of this. So there are some issues with this model. It turns out there's advanced statistical theory that will allow us to handle stuff like that, where we can say, well, okay, we know they can't be equal, modulo that, they seem to act as if they're independent. We know that there are some issues about runs scored and runs allowed being dependent by game state. It turns out these things seem to cancel each other out over a long season. And this is not a bad model. So we're reduced to calculating one of these two, and I've tried to convince you why we want to use the continuous case. So the question is, can we do this sum with this integral in closed form? Well, a lot of it's going to depend on the density we choose, the function we choose to model runs scored and runs allowed. If you had to choose a function in mathematics, what's the easiest function you would choose to do integration? I'm trying to lead you to water. If you had to choose a function, what function would you choose? A horizontal line, thank you, right? Let's assume runs are scored like this on a uniform distribution. So if I want to calculate the probability I score 0 runs, I just integrate from 0 to 1. You need to know a little bit of knowledge in baseball for this question. Why is this bad for baseball? No, it'll allow you to have 0 runs. 0 will declare anything less than 1 will be 0. So you need to know a little bit about baseball to see why this is a bad probability distribution.
Is it not all scores should be an equal probability?
Right, this is saying all scores are equally probable up to 10, and no one can score more than 10 runs. And so this is not a good model. Okay? So again, you need to know a little bit about what the data looks like. And the more distributions you know, the better chance you have of finding one that does a good job of fitting your real-world data. Anybody have any other distributions we can try if a uniform doesn't work?
Parabola?
Could try parabola. Anything else? What kind of inverse function? Are you guys old enough to know about the bell curves and normal distributions? So this is the next natural one to try. Everything in the world is normal. So let's try a normal. We'll maybe put the mean around the average number of scores. There are 2 issues with using this to model baseball games. Can anybody give me one issue? Yes?
Has negative runs.
Yes. No matter how bad the Red Sox are, and they're really pushing it this year, they will not score a negative number of runs. There's another issue with this. So one thing is you looked in this direction and said you can't score a negative number of runs, yes?
So wouldn't higher scores be less likely than the lower scores?
Higher scores would be less likely, but I mean, the probability goes up for a while, then goes down. It's actually possible for the Red Sox in this model to score 1 billion runs in a game. Should we throw away the normal because of this? No. What we can just say is, what is the probability? The probability of the Red Sox scoring 1 billion runs or more in this game is, I think, less than you being hit by a meteor in this class, walking out, being hit by a meteor outside, walking out and seeing your best friend missed by the meteor by 2 inches. Your best friend is lucky. And we have to do this like a couple of times. The probability of scoring 1 billion runs in something like this is so negligible, it's easier just technically to allow it. It makes the integration nicer. Here's another model we could try, the exponential. Nice rapid decay like this. And what's nice about this is it gives you low probabilities of high runs scored, but you could still score 20 or 30 runs. Nothing negative. The problem is it just doesn't fit the data. This says the most likely outcome would be teams scoring no runs. This would be boring. Years ago, Carl Yastrzemski led the majors. This was in the 1960s with like a 301 batting average.
67.
It wasn't 67. I think it was 61. And this was just boring baseball. So what they did is they adjusted the pitcher's mound to help the hitter. They lowered the pitcher's mound. They wanted more action. And so if you look at sports, it's a product. People want you to buy it. They want you to consume it. They want the games to be exciting. People want to be turned in. Now, some people really like pitchers' games. One of my cousins has a friend who went to her first ever Red Sox game a couple of years ago. She left in the 7th inning. It was boring. The other team hadn't even scored a hit. She actually walked out in the middle of a no-hitter, which was then successfully completed. But most, if you have a no-hitter, that's exciting. You saw something. If you have a 2-hitter, not so exciting. And so this is not a good model for baseball. I want to introduce a model that you probably have not seen before, the Weibull function. So it's defined as, have lots of parameters, alpha, beta, and gamma. I have 3 parameters. The more parameters you have in your model, the more dials you have to turn, the more likely you are to be able to find something that does a good job fitting. And so it's defined as x minus beta over alpha to the gamma minus 1, e to the negative x minus beta over alpha to the gamma with a gamma over alpha. This integrates to 1. It's non-negative. It starts off with x is beta or larger. The way you should view it is beta is a translation variable. Any basketball fans here? All right. What's the lowest score you expect to see in the NBA?
Well, didn't the
something like that. So I mean, you would be shocked if any team in the NBA scored under 40. So if you're trying to model runs scored in the NBA or points scored in the NBA, you would not start at 0. You would shift things over to start at 40. Think of it as just Fahrenheit versus Celsius, different scaling points. So the beta is just translating where you want things to start. If you notice, it's x minus beta always divided by alpha. Alpha is rescaling. Think of it as going from meters to feet, or smoots if you are so inclined. The gamma, that's the one that really matters. That's the shape parameter. And different values of gamma lead to very different behavior. What do you think would be a really nice choice of gamma? You're looking at this, what would you choose for gamma? So we've got x minus beta over alpha to the gamma minus 1. Any thoughts of what would be a good gamma that might be easy to work with? Yes? 2. 2 is a good one because then you'll get x minus beta of alpha to the first power. And you'll have an e to the x minus beta of alpha squared that's looking a lot like a normal curve. So 2 is a great choice. There's another great choice as well. Yes? 1, because then you cancel the x minus beta factor completely. So 2 and 1 are actually the best ones to choose. They actually lead to some very famous distributions. So here's what plots of a couple of different ones. If you choose gamma equals 1, you actually get the exponential distribution. So a lot of the very famous distributions in probability are actually special cases of the Weibull. The Weibull arises a lot in survival analysis. If gamma is less than 1, this is something with a high infant mortality rate. Gamma greater than 1, it's something where people are staying in the system for a long time. You can use stuff like this to model purchases on websites, popularity of songs, of movies. So what's wonderful about mathematics is a lot of the same things appear in many different contexts. And if you can learn it in one place, you can apply it in others. Anybody interested in physics here? All right, so I have, I'm a double geek, math and physics. How many people have done gravity in physics? Gravity is what kind of force? It's 1 over? 1 over square the radius. Anybody do electricity and magnetism? What's electricity? 1 over r squared. They're both inverse square laws. And so a lot of the mathematics you develop to solve problems in gravity can be used to solve problems in electricity.
Because I know Gauss's law, right?
Gauss's law.
Gravity or all.
Exactly. They apply, all you do is you just change, oh no, I'm sorry, I didn't mean mass, I meant charge. You just do a search and replace. Much, much easier now. All right. So what I want to do now is I want to talk a little bit about actually using calculus and doing integrals that matter. So most of you, I apologize, you've been spending your time in calculus classes doing integrals nobody cares about. These are designed so that you can become masters at integration. So that now, when you're older, you can actually do integrals that matter. So the first one is I'm going to introduce a new function, the gamma function. So it's defined as the integral of e to the minus u, u to the s minus 1 du. It turns out if you integrate by parts and you choose s to be a positive integer, you get that gamma of n is n minus 1 factorial. This function generalizes the factorial function. It's a beautiful function. It occurs in a lot of mathematics. What's wonderful is the Weibull turns out to be very easy to integrate. And I'll show you why in a moment. You can write down the mean and the variance of the Weibull in closed form without too much trouble. And so, all the slides are online. The lecture will be online. I will post it later today. If you want to do these calculations, it's not so bad. I will quickly try to highlight what's going on. This is why I bought the new green clicker. So if I want to calculate the mean of a Weibull with parameters alpha, beta, gamma, I do my integral, and I have this to the gamma minus 1. All right, so I substitute. I make a wonderful change of variables. If u is x minus beta over alpha to the gamma, then du, oh great, it has this to a gamma minus 1. I then get an exponential function. This is essentially the gamma function from before. So these Weibull integrals can be done without too much trouble. So this is a snapshot from, I think, 2008. Chose a date, someone at random. Okay, well, not completely at random because Boston's listed first. Real estate is precious. When you're at a site like ESPN, MLB, there's only so much stuff they can show you on the screen. They've got to save space for the advertisements. Which statistics do they choose to show? Wins, losses, winning percentage, games back, last 10, streak, interceptions. No, INT is interleague play. How they're doing at home, how they're doing at the road, and XWL is the expected win-loss percentage. What is the team's expected winning percentage? This is one of the key statistics they choose to show you. So I'm going to skip the next few slides. This is another way of trying to model the probability a team wins or loses. If you hit pause now, you can actually watch those slides. Okay, So here's the Pythagorean one-loss formula. So let the run scored and allowed be independent random variables drawn from Weibels. Then the probability that a team wins is beautifully related to these Weibel parameters. And you get the Pythagorean one-loss formula as a consequence. And so we take beta to be -1/2 just so that the bins align nicely. And so what that means is everything from -1/2 to 1/2 counts as scoring 0. Everything from 1/2 to 1.5 counts as scoring 1. The beta is just the translation. It's very nice. Gamma equals 2 is what Bill James suggested. Later numerical experiments where they were just saying, well, what value of gamma does best, gave a gamma about 1.8, 1.82. We'll see in a moment what the best value is. So here's a proof. So I'm going to prove that if this model is correct, then Bill James' formula is valid. The question, of course, is, are my assumptions valid? No. But are they close enough to reality so that this is useful? Yes. This gives us an idea of why this formula is true and gives us some comfort about using it again in the future. You know, how many of you have read David Hume? If you go to liberal arts college, you read stuff like this. You know, just because the sun has risen every day for the past 10,000 years does not mean it will not rise. It does not mean it will rise tomorrow. You'd probably be a fool to bet on not rising, but just because something's happened in the past does not mean it's going to continue. By being able to derive stuff like this from a reasonable model, you get some insights as to what's going on, you get some insight as to why it's true, and some confidence in being able to use it. So given my parameters for the Weibel, I can actually calculate the mean number of runs scored and runs allowed by doing these integrations. I have these relations between the parameters. I don't want to go into all the math, which is strange in a math class. I want to just give you a flavor of how you would do it. So we set up, we want to calculate the probability that x is greater than y. So I integrate over x and y goes up to x goes all the way up to infinity. I substitute in the values, I do my change of variables, and I do the first integral here, and I get a nice exponential. Now what's nice is this is a probability distribution. It integrates to 1. When this hits 1 and I integrate, I just get 1. And I'm now left with this messy integral to do. And now I do a very clever change of variables, and I let 1 over, change of parameters, I let 1 over alpha to the gamma be 1 over alpha rs to the gamma plus 1 over alpha ra to the gamma. And if I do that, I now have something that almost looks like a new Weibel with parameter alpha. For the people in physics, have you seen this equation before? Where have you seen this?
I think with lenses, I think? I don't know.
Could be lenses. It's been so long for me, I don't remember this in lenses. I wouldn't be surprised, though. Resistors. Also for center of mass with 2 masses. So this idea of this kind of like effective quantity, this, adding the reciprocals, this occurs in a lot of problems. And so what we can do is we can recast this integral as integrating a new Weibel with parameter alpha. Ah, crap, we have an alpha rs here. Well, that's not so bad. We just multiply by alpha over alpha to the gamma minus 1. We just do some bookkeeping. And at the end of the day, after some algebra, the formula we want just falls out. And we substitute, and there you go. So this is an application of calculus. This is an application of integration. All right, so we've got 5 minutes left. So I chose a season not at random at all. All right. So 2004. Great, great year for baseball. So here is the best fit Weibels to the data from the Boston Red Sox. This is the histogram of runs scored, the histogram of runs allowed. Does it do a good job or not a good job? And until you take a stats class, that's essentially what you're confined to. So this is one of the reasons why you want to take a stats class and figure out, is this doing a good job fitting or not? Is the Weibel doing a good job? What kind of fluctuations do I expect? So there's a method called the method of least squares. And so bin k is going to be the kth bin. I can look and see how many times do I observe a game where the Red Sox score k runs, how many times do I observe a game where they allow k runs, and I can look at the sum of the squares of my prediction versus the observation. And the reason I'm doing squares is I don't want errors to cancel. If I have one thing where I'm off by a lot in one way and another thing where I'm off by another, by a corresponding amount in the other direction, those 2 errors shouldn't cancel. It turns out absolute values are not good to use in statistics because the absolute value function is not differentiable. If you use squares, you have tools of calculus at your disposal. The better fit I have, the smaller this quantity should be. And that's all you really need to know now, is I have a way of measuring the goodness of fit. The smaller this is, the better fit we get. So now let's look at a bunch of things. So here's the Red Sox. New York Yankees, good or bad? All right, so I got one thumb down. Baltimore Orioles. Tampa Bay Devil Rays. I got a thumb down on this. I mean, look at that beautiful decay. I mean, they may not be winning a lot of games, but they know how. All right. What about the Toronto Blue Jays? All right, Toronto Blue Jays definitely looks bad. But you have to remember something very important about Toronto.
They play in Dell.
Nope. They play in Canada, yes. Could be a metric issue. No, that has absolutely nothing to do with what's going on here. I will actually claim that it's good that the Toronto Blue Jays did not fit the data well. So we're going to do a little bit of advanced theory. Some of you may be going to another class later today. So if you get bored in that class, not this one of course, flip a fair coin 1,000,000 times. Right? Or maybe work with some of the people near you. I think everybody would agree that if it's a fair coin, we expect about 500,000 heads. Would you be surprised if I got 513,218 heads? Does that seem close? Yeah. If I got 688,000 heads, does that seem surprising? It seems a little high. So the real question is, what kind of fluctuations do we expect? Actually, about 95% of the time, you'll be within 1,000 of the mean. So the 513,000, I'd be shocked if it was that large, which means that something's going on here. So if we have 5 teams, the probability that all the teams have good fits that are within the 95%, the probability that at least one of them is not inside the region is 22%. If I go up to 14 teams, which was how many teams used to be in one of the leagues in baseball, 51% of the time, at least one team should be outside this 95% confidence window. If I go up to a 50-team league, 92% of the time, at least one team will be out. If the data is too good, it's probably being cooked. So if you look at the data, I'm not going to go into all the detailed statistical analysis. I'll just say that there's this test called a chi-squared. The lower the value, the better the fit. And about 95% of the time, you should get a value of at most 31.4 for the wibbles, for the runs scored and runs allowed. There's only one team that's really, really bad, and it's the Blue Jays. It turns out, however, that when you're doing a lot of tests, you expect some failure, not through any malevolent issues, but just because of large data sets, because you're doing things a lot. So it turns out there's an adjustment to these tests. It's called the Bonferroni adjustment. And the 31 adjusts to 41.14. If you look at the Toronto Blue Jays, 41.18. Couldn't have asked for better. It's just at the level where you'd start to be maybe a little suspicious. I would be shocked if there wasn't at least one team that was a little bit off. And so this is one of the powers of statistics. It gives you a good language to talk about stuff like this. Is your model reasonable? There's a lot more you can do. There are ways to handle the fact that games cannot end in a tie. I'm not going to go into that. I'm just putting this slide up here so that if you're interested, there are things you can look at. In summary, it's on average, it's about accurate to about 4 games per season, which is pretty good. The predicted value is about 1.74 for gamma. That's very close to the value of 1.82. The median value is 1.76. So just using basic calculus, we're doing a pretty good job of estimating what's going on. The runs scored and runs allowed are not independent, but they seem to behave as if they are. The Pythagorean formula, which is being used by ESPN and MLB, is actually a consequence of our model. And I want to end not with research projects. I can get back to that if people are interested afterwards. Oops. I want to end with this person. So does anybody know who this is? Smoot. Excellent, right? This is the guy from earlier in the talk. Anybody know what happened to Smoot? You know what he did after MIT?
I know at some point he became the head, I can't remember the exact organization, but it was the standards organization.
He became head of the American National Standards Institute. So the fraternity prank ended up having an interesting consequence. He has a very famous cousin who won a Nobel Prize in physics, and I believe to this date is one of only 2 people to win the $1 million on Are You Smarter Than a Fifth Grader? So what I hope you got from all of this is that the mathematics you're learning, you've already learned enough to do useful things. The real question is just what do you want to apply it to? And so when you're trying to decide what classes do you want to do in college, where do you want to go in college, What are your passions? And try to choose classes that can help supplement. So if anybody wants to talk about any of this stuff further, I'm happy to stick around for a bit. Please grab some food on your way out, and then enjoy the rest of the day.